You ever find yourself staring at like a pile of articles or maybe a really dense book chapter trying to figure out something complicated and the main points just are jumping out?
Uh-huh. Yeah, information overload is real.
Exactly. Well, welcome to the deep dive. Think of us as, I guess, your shortcut through that dense material. We grab the sources you're curious about and pull up the really interesting bits you need to know.
And hopefully have a bit of fun doing it. We're basically your guides. Today, we're diving into something quite fascinating, actually.
Yeah, this comes from your interest in Chapter 27 of the textbook, Hyperbaric Medicine Practice.
That's Leon.
And we're looking specifically at hyperbaric oxygen therapy. You'll hear us call it HBO2 for, well, really extreme cases of blood loss anemia.
Right. When we say exceptional, we mean really severe, like a massive drop in red blood cells. Either someone's lost a huge amount of blood, or maybe their hemoglobin isn't working right. You know, the part that actually carries the oxygen.
And crucially, we're talking about situations where the standard treatment, a blood transfusion, just isn't possible. Maybe the blood's not available, or it's too urgent, or sometimes.
Sometimes it's due to personal or religious beliefs. Yeah, that's a key factor in some cases.
Right. So HBO2 comes into the picture here. The chapter calls it a potential short-term therapeutic bridge, like
Yeah.
something to keep things going in a crisis.
Exactly. And what's quite striking is that it generally has a low rate of side effects, which is important in these critical situations.
Okay, so let's get into it. Why is losing a ton of blood so dangerous in the first place? Seems obvious, but maybe not the specifics.
Well, the absolute core issue is oxygen. Your vital organs need a constant supply. The textbook gives some useful numbers here at normal air pressure, like right here, right now.
1 atmosphere.
1 atmosphere, right. Even if you breathe 100% pure oxygen, the amount that actually dissolves into your blood plasma, the liquid part, is tiny, only about 2.3 volumes percent.
Okay, 2.3 volumes percent. Let's unpack that. Like, if you imagine your blood as a container, only 2.3% of the space is filled with dissolved oxygen. That doesn't sound like very much.
It really isn't, because your basic bodily functions, just keeping the lights on metabolically, need about 6.6 volumes percent of oxygen delivered.
Ah, okay, so 2.3 is way less than 6.6.
Way less. Normally, your red blood cells carry almost all the oxygen, compensating easily, but if you don't have enough red blood cells, well, even pure oxygen at normal pressure just can't bridge that gap.
So your body's starving for oxygen, cell by cell, even if you're breathing okay. Got it.
It's like trying to, I don't know, water a massive field with a tiny watering can.
Okay, good analogy.
Yeah.
So how does HBO2 change the game then? How does adding pressure help?
Right, this is the clever part. By putting the patient in a chamber with increased air pressure while they breathe pure oxygen, you physically force more oxygen to dissolve directly into the
You
plasma.
gotta force it in.
Yeah, based on physics principles, like Henry's law.
Yeah.
At 3 times normal atmospheric pressure, 3 atmospheres breathing that 100% oxygen pushes the dissolved oxygen level in the plasma up to that magic number, 6.6 volumes percent.
Whoa. Okay, so just by cranking up the pressure, the plasma itself can carry enough oxygen to meet the body's basic needs, even without many red blood cells.
That's the concept, yes. It's pretty remarkable.
It sounds almost sci-fi.
Well, the source actually uses the phrase life without blood, referencing some really pioneering experiments by Borema back in the late 1950s. He worked with pigs.
Pigs. Okay, tell me about Borema's pigs. What did he actually do?
So Borema and his team, they essentially removed most of the blood from these pigs, getting their hemoglobin levels incredibly low. Then they put them in a hyperbaric chamber at 3 atmospheres, breathing pure oxygen, and replaced the lost blood volume with just a plasma-like fluid. And the pigs survived. They were kept alive just by the oxygen dissolved in that fluid under pressure.
That's astonishing. Seriously. Just oxygenated fluid.
Pretty much. And they tested it further. If they kept the pressure at 3 atmospheres but switched the pigs to breathing regular compressed air instead of pure oxygen, signs of heart strain, oxygen deprivation, showed up on the ECG.
Oh.
But then switched them back to 100% oxygen at 3 atmospheres, and those ECG signs reversed, went back to normal.
Wow.
Then, before bringing them back to normal pressure, they gave the pigs their own blood back, and apparently the animals recovered completely.
That's such a clear demonstration. And this wasn't just a one-time thing. The chapter says others replicated it.
Yes, the authors specifically mention repeating Borema's experiment in their own lab with swine. Same results. Saved the animals' lives.
Okay.
And they even went a step further. They put tiny sensors in the pigs' brains to measure tissue oxygen levels. After inducing a really severe bleed, what they call ACS class 4 hemorrhage, The worst kind, brain oxygen, became undetectable with standard resuscitation.
Nothing there.
Right. Normal pressure, 100% oxygen, IV fluids, still zero brain oxygen measured, but do the same resuscitation with oxygen at 3 atmospheres.
Yeah.
The brain tissue oxygen came up to a measurable level, around 30 millimilli-Hg, the text mentions. And again, these animals survived long-term after getting their blood back before decompression. It just hammers home that HBO2 delivers usable oxygen.
Okay, the animal studies are definitely compelling. But moving to people,
Yeah.
has this actually been used effectively in humans with this kind of massive blood loss?
It has. Though, the evidence mostly comes from smaller studies, case series, not huge randomized trials, but the results are still very encouraging.
Like what?
Well, the first reported success was by someone named Amonik with a patient in shock from chronic bleeding, but a bigger contribution mentioned is from Dr. Hart. He reported on 26 patients, all with that class 4 hemorrhage, losing 40% or more of their blood.
Okay, a really severe group.
Very severe. And they were treated with HBO2 without blood transfusions.
And the outcome?
70% survived, which is pretty remarkable given the circumstances.
70% without blood. Wow.
Yeah. And if you take out the patients who basically had no brain function when they arrived, the survival rate actually hit 95%.
Incredible.
The chapter also details a specific case, a Jehovah's Witness patient, severe blood loss, refused transfusions based on religious beliefs. They were kept alive for days in a Navy decompression chamber using HBO2.
Just on HBO2.
HBO2, fluids, and medications to help stimulate their own red blood cell production hematinics. Kept them going until their body could start catching up.
That's amazing.
And the source notes there are ongoing reports suggesting that using HBO2 early and repeating the treatments leads to success in these kinds of desperate situations.
It really drives home the potential. But you mentioned it's not just about jamming more oxygen into the plasma. The source says HBO2 does other beneficial things too.
Absolutely. It's more complex than just oxygen delivery. Animal research suggests several other advantages. For instance, it seems to help protect the body's machinery for making RNA and DNA, which are vital. It also appears to stimulate erythropoietin production. That's the hormone signaling the bone marrow to make more red blood cells.
So it helps the body rebuild its own supply faster.
Potentially, yes, based on animal models. And in those animal studies of shock, HBO2 also reduced the buildup of harmful metabolic byproducts that accumulate when tissues aren't getting enough oxygen, and aerobic byproducts.
Okay, that makes sense.
Yeah.
But then the source talks about something called reperfusion injury. It sounds complicated. Can you break that down?
Yeah, it's a bit counterintuitive. So when tissues have been starved of oxygen for a while, like after major blood loss, just restoring blood flow can actually cause more damage. That's reperfusion injury.
More damage from getting oxygen back. How?
It triggers a cascade of inflammation and oxidative stress. Think of it like maybe a dry sponge suddenly getting hit with a fire hose. It can cause disruption. HBO2 seems to help lessen this secondary damage.
How does it do that?
The source lists quite a few ways, actually. It seems to switch on thousands of genes involved in repair and reducing inflammation. It lessens the negative effects of tiny particles released into the blood after injury. It makes white blood cells less likely to stick to blood vessel walls, which can block flow.
Okay, less sticking.
Right. It helps protect cell membranes from damage, improves how well immune cells kill microbes, encourages stem cells to get into circulation to help with repairs, and it reduces a specific kind of inflammatory cell death called netosis.
Wow. That's a lot of protective mechanisms. So it's not just oxygen, it's actively helping the body manage the crisis and the recovery.
Exactly. And the source brings it down to a really fundamental level, too. Inside our cells, the mitochondria, the power plants, need a tiny bit of oxygen, like 1 millimilli-Hg pressure, to make ATP, the energy currency.
Right, basic cell energy.
Yeah. Even with severe blood loss, HBO2 can help maintain that minimal oxygen level inside the mitochondria, allowing them to keep producing some ATP, which is absolutely crucial for cell survival during that extreme lack of oxygen.
Okay, that clarifies the how. So we know it can work, we know why it works. When would doctors actually decide to use HBO2 for this exceptional anemia? What are the specific triggers?
The source lays out a few key scenarios. The main one is after that class 4 hemorrhage, the really bad bleed, 40% plus loss if blood transfusion isn't an option. Medical reasons, religious reasons, whatever.
Okay, so major bleed, no blood available.
Right. And then there are specific signs that suggest you need repeated HBO2 treatments. Things like persistent shock, meaning low blood pressure, or needing drugs to keep pressure up.
Makes sense.
Also, if the patient is disoriented or in a coma, if there are ECG changes showing the heart isn't getting enough oxygen, or symptoms suggesting the gut is suffering from poor blood flow, basically signs the body is still in deep trouble from lack of oxygen.
So clear signs of ongoing oxygen crisis. What else?
Another factor mentioned is something called oxygen debt. It's a measure of how much oxygen the body should have gotten during the shock period but didn't.
Like a running deficit.
Exactly. Animal studies link a certain level of oxygen debt to survival chances. And in humans, a high oxygen debt is tied to organ failure and worse outcomes. So measuring that could be an indicator.
Interesting.
And one more point the source raises, even for more moderate blood loss, animal studies hint that HbO2 might actually speed up hemoglobin production.
Oh.
Yeah, which could be really useful in, say, mass casualty situations where blood supplies are stretched thin. Helping people regenerate their own blood faster could be a big deal.
That's a really interesting potential application. Okay, so the decision's made. Use HbO2. What does the actual treatment involve? What's the protocol?
Well, first things first, you still need fluids. Lots of IV fluids, crystalloids, plasma expanders to replace the lost volume. That's standard.
Right, fill the tank.
Exactly. Plus other medical support, maybe those hematinics we mentioned to boost red cell production, antibiotics if there's infection risk, drugs to support the heart if needed, standard critical care stuff.
Okay, and then the HbO2 part?
Yeah. Then, ideally, you start HbO2 treatment as soon as possible, and it's usually done repeatedly. The pressure inside the chamber is typically adjusted based on how the patient's doing.
Higher pressure initially.
Often, yeah. Maybe 2 to 3 atmospheres, breathing 100% oxygen. They monitor vital signs very closely. The goal is to keep relieving that tissue hypoxia, that oxygen shortage, until the body starts recovering, aiming for a hematocrit around 23%, or hemoglobin around 7.7 GDL, roughly.
And you mentioned different chambers, multiplace, monoplace.
Yeah, multiplace chambers are bigger, can treat several patients at once, often with staff inside too. A typical session might involve going to pressure, breathing oxygen for a period, then having planned air breaks, breathing regular air for a short time.
Air breaks, why?
To reduce the risk of oxygen toxicity. Breathing pure oxygen at high pressure for too long can have side effects, so cycling with air breaks is standard practice. They also mention giving nutrition intravenously, but often avoiding lipid or fat emulsions during HbO2 as there might be interactions. Monoplace chambers are for one person at a time, like a clear tube. Similar principles apply: pressure, pure oxygen, and air breaks manage either through the chamber system or sometimes by briefly opening it.
Okay. The chapter includes those case reports, which really drive this home. Let's revisit the first one, the young woman with the gunshot wound.
Right, the 20-year-old Jehovah's Witness. Very severe injuries: lung, diaphragm, spleen, kidney, spinal cord, resulting in paraplegia, unfortunately. Her blood count was critically low before surgery, and she couldn't receive blood.
A terrible situation.
Truly. So after surgery, she got fluids, medications, and they started HbO2 2 atmospheres, 90 minutes, 3 times a day. Initially, her body wasn't making much erythropoietin, that red cell hormone.
So they gave her synthetic EPO.
Yes, exactly. She then had a major setback, an intestinal perforation, severe infection, septicemia, really life-threatening.
Oh, wow. Did they stop the HbO2?
No, they actually continued it, along with intensive care and iron supplements. She ended up having 138 hours of HbO2 over about 28 days.
And the outcome?
Her hematocrit eventually did rise to a safer level, around 22%. And incredibly, despite the paralysis and the sepsis, she survived.
That's quite a testament to the support, including the HbO2, in a situation where blood wasn't an option.
Absolutely. It shows it can be a lifeline.
And the second case, the commercial diver. That sounds like a uniquely challenging setting.
Extremely challenging. A 42-year-old man working under pressure in a saturation chamber, deep underwater, equivalent to 300 feet. He suddenly develops a massive bleed from a duodenal ulcer.
Bleeding out while pressurized deep underwater.
Yeah, and initially they couldn't even get an IV line in him. Breathing enriched oxygen mixed with helium helped a bit at first, but they had to decompress him slowly back to surface pressure.
How long did that take?
3 days. A slow, careful ascent. During that time, they gave fluids under the skin hypodermoclysis, and crucially, they integrated HbO2 treatments into the decompression schedule.
Wow, HbO2 during decompression.
Yes, they managed to get an IV line in eventually, and his hemoglobin was found to be just 2 GDL, critically low.
2. That's incredibly low. Was he conscious?
Remarkably, yes. Stable, Glasgow coma score of 15, fully conscious throughout the whole 3-day decompression, all without any blood transfusion.
Unbelievable.
Once he reached the surface, he finally got transfusions, the ulcer was treated endoscopically, and he made a full recovery. The authors estimate he racked up a colossal oxygen debt during that ordeal.
And the HbO2 was likely key to keeping him stable during that long decompression with such low hemoglobin.
It seems highly probable, yeah. It was a vital part of the supportive care that got him through.
These cases are just, wow. They really illustrate the bridge concept. Now, practicality always comes up. What about the cost? Does the source compare HbO2 to blood transfusions financially?
It does offer a comparison using US dollar figures from around 2016. It estimates that using, say, 4 units of donated red blood cells in the first 24 hours might cost over $2,400, including lab work.
Okay. And HbO2?
For 5 HbO2 treatments in that same 24-hour window, they estimated the cost at around $1,960.
So potentially cheaper, at least for the initial phase.
Potentially, yes. They acknowledge other costs, like intensive care, would apply to both, but it suggests HbO2 isn't necessarily more expensive and could even be cost-effective in these specific scenarios compared to transfusion.
That's important, especially if you think about resource limitations or logistics. Okay, so wrapping up this deep dive, what's the main takeaway from Chapter 27 on HbO2 for this severe anemia?
I think the core message is that HbO2 is a really valuable tool in the toolbox, especially when used early for severe blood loss, where transfusion just isn't happening for whatever reason. Medical, religious, logistical.
Like military field hospitals, maybe?
Exactly. Military settings, maybe remote pre-hospital care if you had hyperbaric ambulances, trauma centers, ERs, even industries like offshore diving, as we saw. It acts as that crucial bridge to sustain life until blood is available or the body recovers.
So from these almost unbelievable life without blood scenarios down to very practical uses in tough environments, this chapter really highlights the remarkable potential of hyperbaric oxygen.
It really does, and it makes you think, doesn't it? Not just about emergencies, but potentially other areas of medicine where getting more oxygen to tissues could be beneficial.
Absolutely. And that leads us perfectly to our final thought for you, our listener. We've heard some compelling evidence, seen the potential benefits. So what do you think are the biggest hurdles stopping HbO2 from being used more widely for severe anemia? Is it cost, logistics, awareness, something else?
And maybe what kind of future research could really nail down its best uses and help unlock its full potential even further?
Definitely some food for thought there. Thanks for joining us on this deep dive.